Vijayabhaskar is a senior engineer for the data communication division at a very short bio from, got 15 plus years experience in the VSI industry. Probably the shortest bio today as well.
Thank you, Mike. Just to let all of you know where we are going with respect to verification. I'm not an ED about tools. I'm going to talk about the verification trends and the forms that the verification is going to take in the upcoming future. Okay, so as usual, the problem statement, right? So we have heard many of the previous speakers talk about we have evolution of chips which are growing like crazy. We had Pentium at 42 million gates way back in 2000. And right now we have 2.5 billion transistors in one chip, right? So that's the kind of evolution the chips are taking, and that's unstoppable. What's the design verification complexity for these kind of evolution is we have like 50 million lines of test bench code. We have 10 plus complex protocols sitting in the same chip, which needs to be verified. We have hundreds of power domains. We have memory and machine requirements to get together on all of this. And then Amit gave a fantastic presentation. How can we bring things together? But what are the common problems, right? So first and foremost thing is most of our chips will have clocks in it, and we'll have trouble, populating the clock across the chip from one component to the other. System Verilog has evolved. LRM has become a lot stricter. It's not helping. The test bench is too slow. So what do we have to solve these problems? Multiple things. Like Amit showed a fantastic slide with lots of solutions in one page. Right? We have try UVM. See how you can improve this speed. Can you move to FPGA? Go tape out the analog part of it, and then get the test chip, and then try to talk to an FPGA with a digital design in it, or some new flow. Right? Somebody comes and says, "Okay, I've tried this new flow, so why don't you try that?" Okay, are these the real problems? Okay, what is the actual problems? Statement is with all this evaluation, right? There is how do we meet the schedule with available resources and have the quality in place, right? Still influenced by. Okay, so with all this new technologies coming up, training is a foremost thing. Not everybody has every skill. When we get together to a project, a lot of skills, a couple of people may have some, may not be trained in formal. So training is problem. So I'm requesting this, I'm taking this opportunity to request managers to plan for training. Unexplored methods. Okay, so there could be lots of problems during writing test benches. The System Verilog that could cause trouble to schedule. Your coverage model, there could be lots of extremely adamant bins which cannot be hit at all, even though you have superpowers of randomization. Okay, those kind of probably a directed test or an other alternative methods needs to be deployed to solve that. Late defect finds. So there could be, because of this randomization, maybe it's for good or for bad, there are defects that are found very late in the cycle. Could that be found it before tape? But it's late. Okay, so that could cause a schedule influence. Verification and validation interdependency. Okay, there are lots of protocols these days where it says, okay, our timeout should happen at 32 seconds. Come on, we cannot simulate 32 seconds, right? So we need to have other dependencies to understand, okay, whether the counter rolled over properly, whether the terminal count was used properly to issue a timeout. Those things cannot be verified in simulation, so we have to depend heavily on validation to do that. Resource. So as I told you, skill is important. So Mike also showed in one of the slides that how difficult it is to recruit people. Subsequent tapeouts of previous chips is going to pull resources back to that project, not at the current project that you're doing. The reason? Because our the technology or the flows were not standardized. Licenses, machines, and schedules. So schedule is a factor which is going to influence your resource, right? Schedule is a factor that's going to influence your quality. And quality is influenced by planning, reviews, incremental learning, and resources. So you see how intertwined these are? So let's see how to solve them. Is there a solution? Yes, absolutely. Why? Because after all, we are humans, right? We have adapted ourselves and grown our technology so much. So how do we solve it? So traditionally, we have an RTL or a mixed signal simulation followed by a gate level simulation and then combined with static timing analysis. It tells us, oh, yeah, I've done everything, whatever I planned. Timing looks good. We're ready to tape out. But that's obsolete because we've seen that the mobile and Internet of Things have pushed the limits up. Like with so much of power domains and protocols that comes up, we need directed randomized RTL and mixed signal simulations. We need integration tests. I'll touch upon this a little later. We need power-aware simulations. We still need gate-level simulations. Many people can still ask, with so much of new technologies coming, do we still need gate-level simulations? Yes, we do. And we need test vectors, okay, to repeat the kind of test that we have done pre-silicon, post-silicon. Plus, we still need all other kinds of structural verification, like CDC. We need formal. We need a pre-silicon validation setup, whether it is FPGA or emulation, it doesn't matter, but we need that setup. We need a test chip. There could be a lot of analog content in your designs which are done for the first time. So obviously we need a test chip to make sure the analog parameters are characterized right. Okay, so then there is a whole lot of things that we need to do so that our cycle time comes as efficient as possible. Mike touched upon this earlier, like requirements-driven verification, where instead of verifying the things that are not required by an application, let us try to first collect what is required by an application. The block can do A, B, C, D, but do we need A and B for an application? Let's try to understand that and have a method by which we can document the requirements from an application scenario. Then let's define our metrics properly. Okay, so how much of code and functional and requirements coverage should I be able to achieve? What is the defect trend? Okay, so we should have a clear way to understand, okay, after my last RTL has been frozen, did I run my regression like 10 times? Did I run my regression 20 times? Is my defect trend coming down? So we should have some clear metrics at the time of planning. Okay. Then the most important these days, with so many newer protocols going into one single chip, is the compliance-driven verification. You may have a lot of test cases, you may have a wonderful coverage model, everything is met, but then the silicon has a bug in compliance. The reason? Because these days all the protocols have to be certified by a third-party test facility. For example, USB is compliant, tests are to be run in a standard facility. Bluetooth, there is a SIG, the special interest group, which is running these tests at the Bluetooth qualified test facility. So we have to take our silicon to these standards body, and then those standards body will run through a set of test cases in certain ways, and that you have to pass that. So one has to consider this upfront during your planning of verification plan to include at least a subset of test or a test which could be simulated in verification. If it is not possible in verification, at least we should have a plan to validate it in emulation or FPGA platform. And because we are putting so many things in a single chip, firmware becomes an extremely important aspect. Protocols like Bluetooth have a huge firmware stack in it, which implements a lot of functionalities specified by the protocol. And given by my experience tells that many times we have a silicon in hand, but you're not able to sell it because the firmware is not ready. So therefore, we have to verify the firmware before even taping out. I would even put the bar that high. The reason, the kind of handshakes between the hardware and firmware, if not addressed properly during verification, is going to cause a major headache. Because firmware also talks to the hardware through registers, hardware also talks to firmware through registers, but there are assumptions made. There are timing assumptions made by firmware, there are timing assumptions made by hardware. So therefore, the firmware verification is extremely important. It may or may not be possible to run a full chips RTL simulation with entire stack running. You may have to plan for validation, or you may have to plan for emulation. Okay. Have we adapted successfully by doing all of this? Probably not. Okay, but I'm sure that we are there. The reason, we are seeing signs of it. Why? Because 10 years back, the designer gives you a document and says, here is the block, go design a test bench for this, verify this completely. With the growth of designs, verification engineers are turning back and telling the designers, no, this is not the way you should design. You standardize your interfaces first. Otherwise, I'm not going to build a reusable test bench. Minimal or no interactions between subsystems. These days, we have lots of processors inside the single chip. So verification engineers or that engineering community is asking the design community to standardize subsystems so that these subsystems don't talk to each other, but they talk through the bus. Whether it is ARM processor or some other processor, but it should talk through the bus. So this way, what we achieved is we can make the block or the subsystem level self-contained, verify that, and reusable across. Test benches that you design for those subsystems can be reused. Now, integration test benches are built automatically. The reason? Because of the need to meet our schedules, our total cycle time has to come down. And the only way to do that is to have test benches built automatically. For example, when you buy a VIP from any EDA vendor, they come with a set of test cases built in. They come with a set of cover points built in, right? So that improves the cycle time. I'm going to extend that a little bit. So whenever you build a block level test bench, make the block level test bench reusable. Make sure that you write your system Verilog code in such a way that so that it plugs into any SoC that this block needs to be used to. And associated with the test bench, I also want to emphasize that the test cases that you have should be in the form of APIs and not using hard-coded magic numbers and stuff like that, so that even the sequences and the APIs that you write are completely reusable, which is built along with the test bench. So what's the path forward? Reuse. That is the key. Given the amazing amount of complexities of the chips, if we don't have reuse in our test bench, we are not going to meet our schedules for sure. So reuse is extremely important, from which can port your test benches from block to system level. Same case with the test benches. So when you have layered sequences, make sure that you parameterize it so that you can reuse across different SoCs. I would even envision to have test benches to build out of spreadsheets. You just tell what is required. Of course, these test benches I'm talking about are SoC level test benches, not the block level test benches. So once you define that this is my SoC, and this SoC has these interfaces, these are the blocks that is required, these are the protocols that are required in a certain format in an Excel sheet, there should be a tool which should be able to, or a script, probably a simple script, which should be able to pull out an existing test bench somewhere in your directory structure and build a SoC level test bench for you. So we need that level of automation. Otherwise, we cannot meet that kind of cycle times. Earlier, we used to design a 2 million gate chips in 2 years. We can't afford that right now. We need a 13-week or a 14-week cycle time, right? So that's the message that I want to communicate to you today, that as verification engineers, we need to emphasize on reuse, reuse, and reuse. Thank you very much.
Thank you.